Okay, sorry. First set of three, the atmosphere, the hydrosphere, the lithosphere. Okay? They each affect global energy transfers in a different way. The atmosphere has the biggest role to play because it is the most fluid. It moves the most easily in response to energy changes, pressure changes, things like that. Okay? And it's in contact with all parts of the Earth, so it does the most in terms of transferring sensible and even to an extent latent heat from one part of the Earth to another. The hydrosphere, okay, its main role is to have the water cycle become part of this energy transfer from one place to another. Okay, so remember that in the water cycle, we drew that, we had the diagram, and then I wrote on it energy in, energy out. Okay, remember that to evaporate water requires a huge amount of energy. So when we have a moist air mass moving from one place to another, that air mass contains untold amounts of energy in the form of latent heat. Because when that water vapor condenses, it will release all of the energy that was used to turn it from a liquid to a gas. Right? We were talking about last week how you can really see that in a thunderstorm. Right? It's high winds, that's kinetic energy, maybe a tornado, okay? Hail, you've got lightning and all of that kind of stuff that goes on in a thunderstorm is all that energy that was used to evaporate the water being released in different forms. Right? In addition to that, as glaciers, which represented water being deposited and stored for long periods of time, as they melt, that water runs down through the rivers, okay, and it causes erosion. And that's work. That's still some of that energy that was used to evaporate them years and years ago, okay, in part of the water cycle. We can build a hydroelectric dam that can harness that kinetic energy of the water. All of that still represents the energy that went into evaporating that water at some point. Okay, so latent heat is still a big part of energy transfer, and it's the part that the hydrosphere, the water on Earth, is part of. The lithosphere was the third part, and the lithosphere doesn't have a big role to play in terms of transferring energy from one place to another, okay, because it just doesn't. It's solid, it doesn't move. But it does provide soil for plants. And it provides soil for plants so the plants can grow, which means the plants can then convert incoming solar radiation from solar energy or light into chemical energy, right? That is one of the second set of three things that we talked about. The second set of three things we talked about was the three fates of light. Okay? If light strikes plants that are carrying out photosynthesis, the light can be converted into chemical energy or sugar. If the lithosphere, the solid part of the Earth that the Earth strikes, is dark in color, then a lot of the energy will be absorbed. Okay? If the part of it is light in color, then a lot of it will be reflected because of the Earth's albedo rates. Okay, so that was what we talked about last week. Okay, that's about as far as we got because there was a lot to cover there. So that's like the quick summary, okay, of last Wednesday's lesson. What we're going to look at now is the last set of three things. Okay, so we got atmosphere, hydrosphere, lithosphere. We got absorption, reflection, conversion, and now we're going to talk about the three ways that energy can move from one place to another. That is by conduction, convection, and radiation. Now, this radiation is not like, the kind that makes you turn green and grow giant muscles when you're angry, okay? It's not like, it is. Gamma rays are a form of radiation, okay? They come from the sun, so are X-rays, so are ultraviolet rays, so is visible light, so is infrared light. They're all forms of radiant energy. That is energy that is transferred by waves, okay? So if you walk up to a campfire, for example, okay, and you can feel the heat coming off of the fire, that is transfer of energy by radiation. Okay? The infrared or heat waves that are coming off of that are a form of wave or radiant energy. Right? The heating system in this room, which we all know is so good, works by radiation. Okay? Along the back wall and along the window wall there are pipes that can be filled with hot water. Okay? When there's hot water in those pipes, the energy of that hot water radiates out, okay, into this room. It's not the most efficient way to transfer heat, but it's what we got. Okay? Anyone have hot water heating in their home, like have like radiators on the walls? It's not very common here. Most of us have a forced air furnace instead. Okay? So radiation is just transferred by waves. In fact, there's lots of places where we use that. Police helicopters always have a FLIR camera, forward-looking infrared. It's the heat camera. So, you know, if there are a bunch of people on the ground chasing a suspect and they run into a forest in the dark, okay, people on the ground they're not going to be able to see them. It's dark, forest, trees are in the way. But the guys in the helicopter, they turn on the FLIR and they can tell exactly where that person is. They stand out like they're made of light because they glow, because they are made of light. They are emitting light we can't see with our eyes, but light the forward-looking infrared camera can see. They're radiating energy, and that camera can see the total shape of a person hiding in the trees. Okay, no problem, because they're the hottest thing in that area. Okay, so it works that way. All right, sort of making sense, everybody? Okay. So radiation is one way. It's how the energy gets here from the sun. Okay, it has to travel through the vacuum of space. It has to do that by radiation. Okay. The other two ways, okay, we'll start with conduction. Conduction plays an incredibly small, almost completely insignificant role in global energy transfers. Okay? It only works in solids because particles actually have to physically run into each other to conduct heat. Right? So it's what happens if you are stirring something on the stove for a long time using a metal spoon. Okay? Eventually, the handle of the spoon is going to get hot. That's conduction. The base of the spoon is in the hot liquid, and it's getting hotter. And the particles in the base of the spoon are starting to move faster and faster, and the faster they move, the more often they run into each other. Okay? Well, eventually, that collision starts to transfer up the spoon. Metals do it best. They conduct heat the best. Okay? And so that movement of particles and of heat eventually gets up the spoon. Right? That's not working on a global scale. Energy that hits the rocks at the equator is not conducting all the way up here. It just doesn't work that way. Does that sort of make sense? It's fine over small distances, but it's not a global energy transfer kind of thing. Okay. Now, is it important for us if we're trying to, harness energy or keep energy from escaping? Would conduction still be something we would have to be concerned with? Is it a way heat could get in or out of a smaller system? Definitely is. Okay. Now, convection, this one's probably the most important. Yeah, we don't have any convection without radiation, but once energy gets here, it is convection that causes the global transfers. Okay. Energy hits the equator, the air at the equator gets warm and it rises. And cool air moves in to replace it. Right? So air gets moving, that's convection. Hot air rises, cool air descends. We use that to heat our homes. Right? Like I said, most of us have a forced air furnace that heats our house at home. Where are all the heating vents on your main floors? Floor or ceiling? Floor. Okay? There's two reasons for that. It's way easier to do all the ducting in the floor. Okay? But also because that's the most efficient place to put them. Hot air comes out from the floor where the air is the coldest. Right? You got hot air moving past the cold air, you get a natural convection current forming in the house that is going to efficiently heat your house. Okay? Part of the reason that the heating system in here doesn't work is because the hot is in the ceiling. Which way does hot want to go? Up. Okay? Now, granted, we're relying on radiation, which is not a circulation, but as it heats the air, as it radiates through the air, okay, the air gets warm and the hot air all goes up into the ceiling. Okay? So it's not great. And if you have air conditioning, your air conditioner uses the same vents, the ones in the floor. Is that very efficient? Now you got cold air on the floor. Okay? You gotta, usually your furnace, if you have an air conditioner, has a higher fan setting for when you're using the air conditioning, because it's gotta blow that cold air harder, okay, upwards so that it can actually get any natural circulation. the way we air condition our houses is not the most efficient way, okay, to do it, but it's what we've got. Right? In the same way that in your basement, your heating vents are probably in the ceiling because it's really hard to run vents through concrete. Okay? Your basement probably doesn't heat all that efficiently. It's probably the coldest place in your house because cold air descends. Agreed? Okay, all that stuff has applications. Okay, give you another example here. Oh, I'm not doing this very well because I have it open. Okay, so I put hot coffee in here in the morning. Okay, this thing does a pretty good job of keeping that coffee hot. Usually by the afternoon it's still warm, and by the end of the day it's tepid, it's not good. But usually I don't have that problem because I drink it before then. Okay? But it does a pretty good job of keeping the coffee hot because it finds a way to limit these three methods of heat transfer. Because the coffee's hot, it wants to go to the colder area, right? But the cup itself is actually quite cool. Touch the bottom there, right? That's got hot coffee in it, but it's cold to the touch. That means it's doing a pretty good job. Now, it's cold here, but it isn't here. It is warm around the top. Now, granted, hot air rises, okay? But the design of this cup, and the design of most insulated cups, is that there's an inner vessel where the liquid is, and then there's the outer vessel, the part that I'm holding right now. In between those two vessels is a vacuum. Right? They literally suck the air right out of it and then seal it so there's no air in that vacuum space. Right? Now the inside of the inner vessel is also a polished metal. What does polished metal do? It reflects. So you've got this inner vessel that's made of polished metal, reflecting the radiant energy, the energy that's trying to radiate out of the coffee and into the surroundings. It reflects a lot of that back. This is why you need to always make sure you clean and polish the inside of that. As it ages, coffee stains it and it gets darker and it actually doesn't insulate as well, so you want to keep it shiny. Okay? So that prevents the radiation, the shiny surface. What does the vacuum layer in between prevent? And convection. If there's no matter in there because it's a vacuum, there's nothing to circulate, right? If there was air in there, you could get a convection current. The hot air would rise, the cool air would descend, it would circulate. Okay? And because it's a vacuum and there's no particles to run into each other, there's no conduction either, right? So it does a pretty good job of all of those things, right? The place where it fails, okay, is here at the top because that's where the two layers come together. Okay? There's the least amount of insulation or vacuum space here. The two layers are in contact, so conduction is occurring. And this is the flaw in any Yeti cup. The top is clear. Can radiant energy escape through a transparent material? Absolutely can. I have not figured out why Yeti has not come around to a different lid than that. Okay, if you get, like I've got another one at home that's a different brand thermos, the top is not transparent and it keeps the coffee hot longer. Okay? It's not as cool, but it keeps stuff from transferring energy a lot better because it does a better job of sealing the lid. Okay? Now, if I've got it like this, it's doing its job as best it can, but I often do this, and I'm drinking out of it throughout the day, is that kind of taking away its effect. Yeah, because now convection can occur, right? Air can get in and out of the inner layer, right? And I'm going to lose energy and all of that. I'll just stop with coffee. Oh yeah. Okay. So is that sort of making sense? Okay. So here's where this is going to come into play. Obviously, you need to understand how those work on a global scale. Conduction does basically nothing. Convection, that's wind. Okay? That's movement of air, circulation of air, and even ocean currents to an extent. And then there's radiation. That's how energy gets here. We know hot objects can radiate thermal energy away. Okay? Here's the other place where that's going to come into play. I'm going to ask you to apply these to a practical situation. Okay? Thinking about how you could either harness them to capture energy and get it into a place, or how you could use them to keep energy out, okay, or keep energy in, as the case may be. All right, so let's look at an example that we always have to deal with, okay, how we keep our houses warm. All right, so this is the wall of your house. Okay, this is inside the house, this is outside the house. okay? And it's December, so it's minus 40. Right? If the wall is hollow, it has nothing in it, okay? This side's hot and this side is cold. Okay? Is there air inside the wall? Okay, so this side of the wall is hot. The air next to this side of the wall is going to get warm and it's going to do what? Hot air rises, yes? Okay, well, if all that air goes up, something has to move in to replace it. That would be cold air from the outside wall. Right? Because that air moved up, so cold air from the outside wall moves in to replace it. And what you end up getting, okay, is a convection current. Air moving within the wall. And your wall is just bleeding energy out constantly and quickly, okay, without anything inside the wall. Now that's obviously not what we do. Okay? What do we put inside the wall instead? Insulation. Okay, so insulation, we all know, insulation's job is to keep the house warm. What we're concerned with today is how. What does insulation do that keeps the house warm? Or rather, keeps the heat in and doesn't allow it to transfer out. What's fiberglass made out of? Fiberglass. Okay, what's insulation made of? It can be made out of fiberglass or it can be made out of something else. What's the other material it's commonly made out of? You probably hate the sound of it. It's rubbing together. You guys don't have as much experience with this stuff because it's bad. Styrofoam? You guys are styrofoam. Okay? Those are basically the two types of insulation that we use. All right, now fiberglass is exactly what it sounds like. It's a whole bunch of tiny glass fibers, and they're just interwoven, and it looks like a bird's nest. You know, like birds intertwine the sticks and straw and grass and everything to make their nest. That's what insulation looks like. If you could see it almost at a microscopic level, you would just see all these fibers, okay, that are interlocked together. What's in between all the fibers? Air. So I still have air inside the wall. I had air before. Why is this better? What can the air not do now? Can't move. It's trapped in between all those fibers. Okay? So when you put all these fibers, there's all these spaces now between the fibers that are filled with air, but the fiberglass doesn't allow the air to circulate now. It can't move, it's trapped. That makes it an excellent insulator. Conduction can't happen through air because air isn't a solid, right? And now that the air can't move, convection can't occur either. So it does a great job of insulating your house. Now, it's not doing anything for radiation. Okay? Can energy still get through your wall by radiation? It absolutely can. But there are things you can do to help it. What color would be best to paint your walls? If I want to keep the radiation in. In other words, I want to reflect it. What color would be best? White. Okay? That's why generally house walls default to some light color. Okay? Not generally white, because white's actually kind of jarring, okay, to have a wall that's totally white. But they're generally going to be light in color because that's going to reflect. Styrofoam boards, okay, insulation styrofoam boards, actually have foil on both sides. Okay? Foil on the inside prevents heat from getting out. Foil on the outside prevents heat from getting in the summertime. It helps keep your house cooler. All right? They don't generally do that with fiberglass. Not sure why it would work, but they don't do it. Okay? That sort of making sense? Okay, something to know about tinfoil. How many people have used tinfoil before? Okay, baked potato? Okay. I don't know if, I didn't realize this, but most people don't know how foil works. Okay, look at this side of the foil. They're different. Why? This side is shiny. This side is dull. Why are they different? Why aren't they both shiny? What's this side going to do to heat? It's going to reflect it. What's this side going to do? It's going to absorb it. The dull side absorbs heat. It absorbs radiant energy, which is what your barbecue or oven is giving off. Okay? You've got a heating element or a fire that's radiating energy towards the potato. If you wrap the potato with this side out, after an hour you are going to have a raw potato, which is gross. Okay? You will have like your sour cream and chives and bacon bits and all that goodness ready to go, and you're going to cut into this raw potato and be sorely disappointed. Okay? Look guys, I've been to a lot of barbecues and I've seen a lot of people do this wrong. Okay? I always watch the person who's doing the baked potatoes, and I can tell right away if they have no idea how foil works, because they got like 20 potatoes and half of them are shiny side out and half of them are dull side out. And I always go, that's my potato right there. Okay? And I pick the biggest one that's got the dull side out, because I know that one's going to be cooked. Okay? The other ones are going to be raw, and then people are like, I don't understand, they've all been on barbecue for the longest, and I just face palm. Okay? Now you will never be embarrassed at barbecue. Okay? This side is the absorbing side. Okay? If you're cooking something in the oven and you're lining the pan, okay, just to keep it, so you don't have to do dishes, you just have to throw away the tinfoil. Lots of people do that. Shiny side facing the food. Okay? Dull side on the pan. Heat from the bottom gets absorbed. Heat from the top gets reflected back to the food. Brilliant. Okay? Science in action. Tinfoil has two sides. Now, if you have an emergency, like a roadside emergency kit in your car, you'll find a blanket in there made of this stuff. Okay? Which side should face you if you're wearing it? Shiny side. Okay? It'll reflect your radiant energy back to you, and they work surprisingly well. And if you've ever put one on, you put that shiny side to work, and you get hot. Your own heat just keeps coming back to you. Okay? And it does a really good job. It doesn't prevent convection at all. Okay? That's what a real blanket does, right? If you put on a real blanket, it's interwoven fibers of cotton or synthetic or whatever, and there's trapped air in between. Standard blankets, they prevent convection, right? Or if you have a down-filled blanket or a down-filled sleeping bag, those are the best. Down is the best insulator you can get. Okay? Goose feathers. Right? I mean, evolution has been working on keeping geese warm for thousands or millions of years, and it's got it pretty much figured out. Goose down is incredibly good at insulating, and even works when it's wet. Well, because geese, right? It works even when it's wet, right? It's one of the best things, because all those little barbs in the feather, they interlock, they trap air. Okay? If you want to prevent convection, you got to keep the air from moving. If you want to harness convection, you got to get the air moving, or the water moving, whatever it is that you want. Okay, is that making some sense? Okay, so it's going to be some kind of practical application kind of thing that I'm going to ask you about with conduction, convection, and radiation. All right, let's talk about an example where we want to capture energy. Let's say I want to heat water using the sun. Okay, so what color should I make the capturing part of that? Black. Yeah, I want to make it black because black absorbs radiant energy. If I'm going to use the sun to heat water, I need whatever the water is going to be in to be black, so I absorb as much energy as possible. Okay, typically in a solar water heater, it's not just like a big box that's black full of water. That's not efficient. What typically you have is a container of water somewhere, and then pipes leading in and out of it. All right? There's a pipe going out the top and a pipe going out the bottom. Those are usually made of copper. Why would we use copper? Copper is an excellent conductor. Any heat that's captured by this heater is going to go through the copper and into the water very easily. Right? I don't want to use a material that doesn't conduct heat. It's like, would you make a pan out of a material that doesn't conduct heat? That'd be pretty useless. You put that on the stove and it wouldn't transfer any energy through to the food you're trying to cook, right? It doesn't make any sense. So we use copper, and usually what they do is they just make a whole bunch of like folds or whatever in the copper, just so it weaves like this, and they paint it black. Sun hits those copper pipes, and the water will start to circulate on its own. Okay, because you got this big tank back here that's got cold water in it. You've got this part facing the sun that's capturing energy because it's black and it's got copper in it. Okay, and so that water gets hot. Okay, it naturally moves to the top part of the container. Cold air gets pushed out the bottom back into the heating apparatus. You don't even need a pump. It'll circulate itself just using the second law of thermodynamics. Okay? What if you got stranded in the wintertime and you wanted to keep warm, but you couldn't start a fire? What would you do? Yeah? Okay. Anyone ever built a Quincy before? Okay, so a Quincy is basically an emergency snow shelter. What you do is you make a pile of snow. Don't pack it, you just make a pile. And then you hollow it out and crawl inside. Right? Why is that going to keep you warm? Snow is cold, isn't it?
Snow's white.
Snow's white, so it's going to reflect your radiation back at you. It is. It's an excellent insulator. In fact, it looks just like fiberglass insulation at a microscopic level. You know how there's that saying, no two snowflakes look alike? And they all have kind of a snowflake shape? Well, those edges, when the snow lands, it locks together. What's trapped in between the snowflakes? Air. That air can't move. It's trapped, just like fiberglass. Okay? When I used to teach in Lloydminster, we taught the Saskatchewan curriculum. One of our units was a snow ecology unit. I'd wait till it was minus 30, okay? And then I would take my kids out to the football field, and we'd build Quincy's. You'd be surprised how fast people can make a pile of snow when it's freezing cold outside and it's their only hope of warmth, because they wouldn't let them come back in. Okay? They'd make these piles, and then they would haul them up, you'd crawl inside. You get 2-3 people in there, and the thing will start to melt on you. Okay? It'll literally get that hot. Right? So it's a great insulator. Same reasoning though. Okay? If I can trap the air, I can prevent heat loss by convection. Making sense? It's all about how can I harness or how can I prevent these things. So there'll definitely be a question about that on your unit exam, probably the final exam as well. You got to think about radiation, convection, conduction. You got to think about absorption, reflection. You got to think about albedo. You got to work all those things together to solve a practical problem. Okay. Now, that's for atmosphere, okay? Now we're talking about hydrosphere, okay? So the hydrosphere, we said in the water cycle, energy gets transferred because of this stuff, latent heat, okay? The energy that's trapped in materials because of their state. Okay, so in the water cycle, we said that to evaporate water required a lot of energy. Okay, and we wrote on the picture of the water cycle energy in here. Okay, when that water vapor condenses, okay, falls as precipitation. That was energy out. So within the hydrosphere, we're talking about latent heat, state changes. That's where the energy comes from, or the energy transfers occur within the water cycle. Okay, you very rarely see this one. Okay, sublimation requires a huge amount of energy. To take ice and turn it directly into a vapor, at least for water, you just don't see that. Okay, right? But we do see deposition. Okay, remember in the wintertime, a couple of times we got the hoarfrost? Okay, we got the ice crystals all over everything. All the trees looked like they were made of white ice and snow and stuff. They look really cool. Okay, that's deposition. That's water vapor condensing and, well, actually not condensing, freezing directly onto an object. Right? So a lot of energy is actually released in that. That's why it gets foggy when it's going to happen. Right? There's all this vapor in the air. Okay? And then you get that deposition happening. Right? Dry ice does this. So carbon dioxide doesn't exist as a liquid. It always converts directly from dry ice to carbon dioxide gas. Right? It just skips it, it sublimates easily. Right? All right, everybody okay with that? So within the hydrosphere, it's all about latent heat. It's all about the water cycle and where the energy goes in and out. Okay, and then for the lithosphere, again, it's not big on energy transfers. It's bigger about conversion and absorption. It's about albedo. It's about providing soil for plants so that plants can convert solar energy directly into chemical energy. Okay, that's the role of the lithosphere. Okay, we wrote that down the last time, right? The 3 fates of light. All right, I'm going to give you guys a little break here, and then we'll get into the lesson on wind patterns here in about 3-4 minutes. All right, so what we're going to look at in this lesson here is how all the convection stuff we just talked about, how that plays into transferring energy on a global scale, because we said that's the biggest way that energy gets from the hot equator to the cold poles. Right? It's by convection, it's by this moving of air. But it's not just as simple as the hot air goes to the poles and the cold air moves downwards. It's not one convection current. It's more than that, because the system is more complex than that. Right? The biggest complicating factor would be that the Earth rotates. Okay? The atmosphere and the Earth don't rotate together. The Earth actually rotates under the atmosphere. So the atmosphere can be doing one thing, and the Earth can be rotating underneath it, which can kind of skew or deflect our sensation of which direction the wind is actually coming from. Okay? And it's why we have the patterns of prevailing winds that we have. Around here, prevailingly, the weather or the wind comes from the southwest. That's due to our latitude. It actually has very little to do with the fact that the mountains are there. Yes, they can produce Chinooks and all that can happen, but we don't get a Chinook every day. We get Chinooks sometimes. Prevailingly, our wind still comes from the southwest. If we get wind from any other direction, a change in the weather is coming, because that's not what prevailingly happens. Okay? And we say prevailing because it's not all the time. There's also changes in pressure. Right? There's high pressure areas, low pressure areas, those can move around and they can cause changes in the weather as well. If that's happening, then our wind would typically come from a different direction and we would get some sort of weather change. And there's things like the jet stream and stuff like that that we'll talk about that can help to move that energy around. It's not just as simple as hot air rises and cool air descends. Okay? All right, so we're going to talk about that. We're going to talk about the Coriolis effect. Okay, that's the rotation of the Earth. Okay, and it's actually the combination of convection and the Coriolis effect that cause the wind patterns that we see. All right, so first point, the Earth is round. Okay, none of this works if the Earth's not round, and by the way, the Earth is totally round. Okay. You're a flat earther, you're going to hate everything I say all the time, and that's because you're wrong. Okay? So, there's just no nice way to say it. So, we've got the Earth. The Earth rotates this direction. Right? It's why the sun comes up in the east and why it sets in the west. Right? So, if the sun is just about to rise, the Earth is going this way. Okay? We're in the dark. We're over here somewhere. Right? And as the Earth, right over here. Okay, so we'd be over here somewhere in the dark. As the Earth rotates around, we come into the light. Okay, so it looks like the sun is over there because from our perspective, it is. Okay, so it rises in the east, and then as we spin underneath it. Okay, it appears to do this in the sky and then set over there, right? But the Earth's atmosphere is trying to move north and south because that's where the temperature differentials are. As we move underneath the Earth's atmosphere, and the Earth's atmosphere is trying to do something else, we feel the air moving in the same way you would feel it moving, not that you would do this, if you stuck your head out the window of a moving car. Okay? It feels like it's windy, even if it's not. You're just moving through the air at a high rate of speed. Well, you're doing the same thing on the Earth as the Earth rotates. Okay? You're moving through the air at a high rate of speed. The air is not moving with you. Okay, does that sort of make sense? Okay. So even if air is trying to go north-south, we would actually get a sensation that it's coming from the east or the west because of our rotation. Everybody all right with that? Okay. So there's lots of reasons that air can move. Obviously, the second law of thermodynamics is the biggest one. Okay, energy flows from hot to cold, so it's going from the equator to the poles. But another thing that can move air is pressure. High pressure to low pressure. That's going to cause air to move as well. Okay, usually when we get really strong winds, it's because there's some difference in pressure. Maybe you're one of the people that is very sensitive to changes in air pressure. Okay, when we have a Chinook, lots of people get migraines. Okay, my wife gets migraines when we're getting a Chinook because she's sensitive to the changes in pressure. When we're getting a Chinook, the pressure is very high, but it's changing quickly. That's why the wind is blowing. The high pressure near the mountains is trying to equalize to the low pressure on the prairies. Okay, and it blows through, okay, and we feel that. Okay, it's a result of a change in pressure. It's not a result of a change in temperature. So that's the other reason why we can get air moving, is because there's high pressure and low pressure areas. Okay, so the jet stream is something we definitely need to know about. So it's in bold here, okay? It is a major wind mechanism. It is created by differences in temperature and, I should say, and pressure between the polar and tropical regions. This is its role. What I've written here, this is the role of the jet stream in terms of energy transfer. Okay, so you should definitely add it to your notes somewhere. Okay, the jet stream moves latent heat. Okay, it transfers latent heat. That's stuff within the water cycle by moving moisture-laden air masses. It can push them around. Now, we don't feel the jet stream on the Earth's surface. Okay? The only place on Earth where you could ever feel the jet stream would be if you were above 10,000 meters. So top of K2, top of Mount Everest, something like that. Okay? It is a very high altitude wind mechanism. That said, it can do a lot to move air masses around, and its location changes as a result of pressure. Most of the time, the jet stream just kind of does what this diagram says it does here, which is it just kind of oscillates up and down like a sinusoidal wave, okay, across the northern hemisphere when it's under normal conditions. Okay? Differences in pressure can change the location of the jet stream. And when its location changes, then different kinds of air masses, maybe ones that are hot and dry, or cold and dry, or warm and moist, okay? They can move them all around, and that's what's going to cause your changes in weather. So, in this particular day, okay, we have an unusual pattern of the jet stream. Okay? It goes from looking like a sinusoidal wave to going back on itself, going back out into the ocean, and then coming back. That's strange. That can produce a rapid change in the weather and unsettled conditions, kind of like what we're supposed to get today. Okay, we're kind of in an unsettled situation right now, weather-wise. We're supposed to get some thunderstorms later today, okay, things like that. So, in this situation here, the jet stream is coming off of the Pacific, okay, and there's a high pressure area right here and another one here. So this is blocking. They call it a high pressure block. Okay, and it's blocking the jet stream from going like it should. The jet stream wants to do this, but it can't. This high pressure area is pushing it back and not letting it go that way. All right, so it goes around this high pressure area, and there's a high pressure area here. They're trying to equalize, right? You can't have high everywhere, right? So what happens is there's this channel in between where cold air from the Arctic is pushed downward rapidly. There's a pressure differential that's trying to equalize. So you get a lot of wind, and that's carrying chilly air. Well, because the jet stream has just come off of the ocean, it's got a lot of moisture with it. It goes around this, okay, pulls this air down, goes back out over the ocean and picks up more moisture before trying to come back in to the land. So this tropical air is moving in, tropical air from here, and you got this whole green area here that they've labeled unsettled. Well, they should have also labeled in here unsettled. Okay, so this is going right across. What states are those? Here's your U.S. geography test. Oh, and you got another state. Right across here. Midwest, yeah. Oklahoma, Ohio, Kansas. Well, we're not in Kansas anymore because that's Tornado Alley. The jet stream very frequently goes across that part of the United States, causes unsettled conditions. Okay? That's usually the bottom of one of those sinusoidal waves. Well, guess who else usually ends up in an unsettled area? The Tornado Alley of Canada, us. Okay? We are in what is known in insurance circles as a hail belt. Okay? We get hail more often than most places do. Okay? Significantly more often, because we're just in this area where the jet stream typically moves through. Okay? But if the jet stream does something weird and moves back and forth or gets its shape changed, then we get different weather conditions. In the wintertime, if this happened, that would be like one of those big snowstorms where it drops 25 centimeters, but we still have to come to school. Well, okay, I do. You guys can stay home, and you should, okay, in those situations. Okay, making sense? So the jet stream moves moisture around. Moisture contains latent heat, and that's lots and lots of energy, right? So convection, that's moving the sensible heat, the hot air. The jet stream is pushing the moisture, okay, the latent heat part, right? So they both have a role to play. So let's say if on a unit exam I ask you, hey, how does, talk about some of the mechanisms that help move heat from the equator to more northerly areas. You could certainly talk about convection, but should you also talk about this thing? You definitely should. It would probably be 2 marks out of 5, okay, to say jet stream and what it does. All right, now, in terms of wind patterns, so now we're out of the jet stream, we're just back to straight convection again, okay? 2 things cause the prevailing winds that we have. The Earth rotates because it's round, okay, and convection. So, at the equator, we know that more energy hits the equator than does the poles. So it's hotter at the equator than at the poles. So air at the equator heats up and it rises. So you can see in the diagram here, okay, we got hot air and it's moving up. Right? There's cold air above, okay, and it pushes it north. When this hot air comes up, it pushes that air north, and then there has to be some air move in to replace. But the hot air goes up, something has to move in to replace it, or it would create a vacuum. Okay? Can't have that. So, okay, air from further north moves in to replace it. This air is cooler than this air. So we have some air coming from the north trying to move south along the surface. But the Earth is rotating this direction. So it makes it feel like the air is coming from the northeast instead of from the north. Okay? So much so that it actually feels more east than northeast. Right? We call this wind pattern, or this part of the wind pattern, the trade winds. Okay? They're on either side, north or south, of the equator. Right? The reason we call them the trade winds is because that's what they were used for in history when we only had sailing ships, okay, to move stuff from Europe, okay, to the New World. So what would happen is people that were doing the trading would sail south, okay, along the coast of Europe. They'd pick up all their goods, whenever they get to like Spain, Portugal, North Africa maybe, okay, and then they would start to go towards the New World. They would catch the trade winds because they drop below the horse latitudes, okay, and they'd use the trade winds to go to the New Worlds. They'd end up in the Caribbean, okay, and they'd sail north and do some trading along the Caribbean, pick up some stuff from the Caribbean, come into the New World here, drop off a lot of the stuff they brought, pick up beaver pelts and whatever we would trade back to Europe, okay, and then they would take the westerlies back to Europe. Okay? That would be your pretty standard trade route. Okay? But it's all the result of the fact that the Earth rotates under convection. So near the equator, okay, hot air rises, cool air moves in to replace it. We've got this convection current. Okay, further north, okay, when this air gets to here, it's now cooled off, and it's settling down into the void that was created by this air moving south. As it does that, it gets kind of pushed this direction, because compared to this air, it's still warmer. Okay? So it moves along the surface, okay, and then goes up when it's given the opportunity. Okay? And that actually gets deflected this way. This is the part of the world that we live in, okay, where the winds are from the west. As you get closer to the pole, sorry, I'm going to delete all my drawings here again. As you get closer to the pole, that air that's been moving north is actually still warm by comparison to the air up here, so it's forced aloft. Air from the pole, which is cold, moves along the surface, and you've got the same thing going on at the pole as you have at the equator. You've got easterlies, whereas here in the middle, you've got westerlies. Right? So what you've got to be able to explain is convection's going on. Hot air rises, cool air descends. The Earth spins underneath it. That causes a deflection. Okay? Everyone with me so far? Okay. So now what I'm going to show you is how this deflection, this Coriolis effect, works. Okay? Now, I got my friend here, Wilson. Okay? You guys seen Castaway? This is Wilson. I don't talk to him in front of other people. All right, so Wilson is going to be the Earth. Okay, and I'm going to demonstrate to you how this deflection happens, because sometimes it's easier to kind of visualize it when you can actually see it happening. So Wilson's the Earth. The Earth rotates like this. Okay, now wind is trying to go from north to south, but the Earth is going to spin underneath it. So I'm going to really concentrate here and focus on doing two things that are different at the same time. Okay, so I'm going to move the marker straight down the ball, but as I do that, I'm going to rotate the ball. Okay, and you're going to see the same thing that happens with air happen with the line that gets drawn. Okay? I didn't draw like that. I didn't move the marker like that. I moved the marker straight down the ball. But because the ball was rotating under the marker, I got a deflection. Okay? The Coriolis deflection, which is what we see with all the air moving on Earth. Okay? It's exactly the same thing. All right. Give me a minute to think about that. I got to clean Wilson up. I only get to spend money on one ball. Okay. Now, on Earth, there are 3 bands of wind, okay? Because the Earth is a certain size and it rotates in a certain way and at a certain speed. Okay? We can't really see those because the Earth's atmosphere is transparent, but we can see it in the movement of storms. Okay? Hurricanes typically track the same way the winds go. Okay? They move in, at least in North America, they move in along the equator, moving as the winds would deflect them, and then as they hit land, they usually move up the coast, and then when they get to this part, they get kind of just petered out, right? But they do generally move in the same direction as the winds would blow. Okay? Now, if you had a planet like this one, whose atmosphere is not transparent, you can actually see the different bands form. And you can actually see them moving in different directions. If you ever watch a movie of Jupiter, it actually looks like some parts of it are going one way and some parts of it are going another way. And they are. That's just the winds. Jupiter rotates only one way, but the winds go in different directions. In fact, this very famous storm right here is right on the verge. Like it basically makes up the whole band that it's in. One side of it is on a band moving to the east, one side of it is on a band moving to the west, and those feed that storm and keep it rotating. Okay? That's why that storm has been raging for as long as we've been able to look at Jupiter. Okay? We're talking about hundreds of years, and it shrinks sometimes and it gets bigger sometimes. They're actually thinking it might actually be on its way out. But this is a giant hurricane that has been raging for hundreds or maybe even thousands of years. And you see all kinds of other spots on Jupiter. Those are storms too. They do the same thing. They're just not as big as this, as the big red spot. Okay? Now, part of the reason Jupiter does this is it's big. Okay? Part of the reason is its atmosphere is made of hydrogen, which is lighter. And the other reason is it spins really fast. Okay? It takes Earth 24 hours to make one complete rotation. It takes Jupiter 10 and a half. Okay? So way bigger planet, and it rotates completely in 10 and a half hours. So you get 5 hours and 15 minutes a day, 5 hours and 15 minutes a night, and it's the next day. All right? That can create winds moving at hundreds of kilometers per hour, okay, all the time because of that extra energy of that rotation. Okay? It's not like Jupiter gets a lot of sun, right? It's quite a bit further from the sun than we are. All right, so the Coriolis effect. Okay, so the Coriolis effect, we kind of explained already. I demonstrated it there on Wilson. Okay, if air is trying to move from north to south, the Earth rotates underneath it this way, and it gets deflected. If it's trying to move from south to north, as it does at our latitude, okay, it gets deflected. So it's a westerly wind instead. By the way, if that seems weird, like I've been saying easterlies and westerlies, remember that winds are named for the direction they come from, not the direction they go. Our winds are westerly, even though they blow to the east. Okay? They come from the west. Winds are always denoted from their source. Okay? So these are westerly winds here. So if we're seeing that there's a pattern like this on Earth, is that another way that latitude affects climate? Right? We talked about all those factors that affect climate. We only talked about latitude from an energy perspective, right? The further north you are, the less energy you get, so it's colder. But latitude also affects wind, right? And wind is one of the 4 components of climate. Are you following my intertwined thoughts here? Okay, these things are all related, right? When we say latitude affects climate, it's not just temperature, it's also wind, it's also light, okay? Everyone okay with that? Not so much precipitation, but it's definitely the other ones. All right, so we get that Coriolis deflection, okay? And there's another part of this too that plays a role here. The Earth rotates like this, right? So if you're, sorry, easier to demonstrate with the ball. If you're at the equator, it takes you 24 hours to go all the way around to here again, right? If you're here, further from the equator, it still takes you 24 hours to go all the way around. Who went further? Which circle is bigger? This circle that's at the equator, or this circle up here? I just rotated it the wrong way. Which circle is bigger? Equator. The equator. It takes the same amount of time. Someone at the equator goes further in the same amount of time, so they're going faster. That's why the deflection is greater near the equator. You're going faster. The effect of that rotation is greater at the equator. You're moving underneath the atmosphere at 1,600 kilometers per hour. Okay? You're at, our latitude, and it's more like 800 kilometers per hour. Okay? It's significantly different. So the effect of that deflection lessens the further up you go. All right, so we definitely need to know Coriolis effect. Okay, that's the deflection of any object from a straight line by the rotation of the Earth. Okay. All right. So fair for me to ask a question on a test that said, explain using your knowledge of wind mechanics and heat transfer why there are patterns of prevailing winds on Earth. Okay, what should you talk about in that answer? Should you talk about convection? Okay. Should you talk about the Earth's rotation? Okay. Should you maybe name some of the winds, like trade winds, okay, or westerlies, or polar easterlies? Okay. Would you mention jet stream in that answer? If I showed you a diagram like this, like this one, jet stream's not really part of that, is it? Okay? The jet stream actually goes against patterns of prevailing winds, right? It can make the wind come from a different direction, short term. Okay? Long term, patterns of prevailing winds, okay? That's convection, that's the Earth's rotation, okay? All of that stuff. Okay? Latent heat and jet stream would be more part of, in general, how does energy get from the equator to the poles? Then jet stream is part of that. Okay? But if we're talking about prevailing winds, jet stream is not part of prevailing winds. Jet stream is part of short-term changes in weather. Okay, I would like you guys to take some time and write good, complete sentence answers for those 4 questions. Okay, and then we will talk about them here in a little bit, and then you might even get a little bit of time to finish up that climate activity, okay, if we're done a little bit early.